last time's lecture will not be posted because I didn't hit the stop record button before the turn off button, and so it corrupted all the files and they're unviewable. And even if I really tried to remember to record everyone, that'll happen embarrassingly frequently because I can't use a machine. So let's think about this. So we have a formula which says that the solution to something like ax squared plus bx plus c equals 0 is, well, just really easy. You can just write it down. And that's like, in fact, a super old formula that was basically known at the very least by the ancient Egyptians. Which is noteworthy because they didn't even necessarily have the formulaic sophistication to write down a formula like that. So you might say, well, if I have a formula that solves that, why not something that solves something that's 1 degree higher? Ax cubed plus bx squared plus cx plus d equals 0. And indeed, there is a formulaic way of solving it. Cardano in the 1540s produced a solution. His solution kind of involves reducing it to what's called a depressed cubic with b equal to 0 by doing something a lot like completing the square, and then figuring out how to solve things like that. And an extra credit that is posted for today will show you that formula. When you see the formula, you'll see why I'm not showing it to you here. It's too long to bother writing down. But it works. It solves an arbitrary degree 3 polynomial. A few decades after that, Ferrari produced a solution to an arbitrary degree 4 polynomial. And if you write down the formula that he gave just raw, you probably won't be able to fit it on a single sheet of paper. So I mean, it's an unreasonable formula to try to use just by hand. So that's great. I mean, on the other hand, like if you want to use a computer doesn't care how long the formula is. It'll evaluate it quickly enough. But there was a movement after that to say, well, why does this have to stop at degree 4? Can we solve an arbitrary polynomial equation and get maybe a stupid, complicated formula, but still a formula? In the 1820s, a mathematician named Galois, age 19, invented a new field of mathematics. It's now called Galois Theory. And he used this machine he built to prove that most degree 5 or higher polynomials cannot be solved by any combination of algebraic manipulations. So there is no quintic formula. And in fact, his machinery is pretty robust and even shows that there's a degree 5 polynomial that you can't write down a solution to using any combination of addition, subtraction, multiplication, division, powers, and roots. There is no solution to that that uses only those ingredients. So the best you can do is approximate solutions. If you wanted to approximate the solutions to that, how would you want to go about it? If I asked you, where about are the x-intercepts of that graph, how would you want to do it? If you're allowed to use a machine. Well, how about graphing? Do you think you could have a computer graph that? Yeah. And then do you think you could just see where an x-intercept is? And you might only be able to get it up to around somewhere between 1 and 2, but then you could like zoom in and only plot between 1 and 2. Maybe it looks like it's at 1.5. Then you could only look between 1.4 and 1.6, and you could get increasingly good bounds. So this isn't what we're going to do today. But I will point this out. You still have approximate methods. For example, graphing. Right, you can look at a graph and get approximations to that solution, but you will never know exactly what the solution is. You can only know it up to the first 1,000 digits. Sorry, that's super illegible, isn't it? Yeah. All I'm saying there is that you still have approximate methods. You can still graph and find solutions. So what this means in some sense is if I give you a high degree polynomial and ask you to find the solutions on the nose, you might immediately say this is obviously an unfair question, because there's no general technique. Instead, what we'll develop today are a few tricks that work sometimes to solve high degree polynomial equations. And the first of these tricks says that, well, as soon as you know a solution to a polynomial equation, if you have a degree, say, 3 polynomial, as soon as I give you one solution, well, there are only 2 more left. And so those 2 other solutions, those should correspond to like a degree 2 polynomial. But you know how to solve degree 2 polynomials. So here's the game. If you find one solution, you can find a corresponding factor and reduce to a simpler equation. So here's one. 2x cubed minus x squared minus 7x plus 6. I claim that has x equals 1 as a solution. Does it? What do you get when you plug in x equals 1? I guess you get 2 times 1 cubed is 2, minus 1 squared is 1, minus 7 plus 6. Does that add up to 0? Good. So it does actually have x equals 1 as a solution. That's worth checking. This means that this polynomial, x minus 1, must divide evenly into 2x cubed minus x squared plus 7x plus 6. How do people feel about polynomial long division? How many people have a memory of polynomial long division? Okay, so the first thing I'm going to do is, what if I change polynomial long division to synthetic division? How many people are happy with that? Okay. There is posted to the webpage right now a walkthrough of how polynomial long division and synthetic division work with a single example done in excruciating detail. If you want to check that out, check that out. There's also the appendix in the book. I'm going to just do the example really quickly. So I want to see how many times x minus 1 divides into that. That is, I need to compute 2x cubed minus x squared minus 7x plus 6 divided by x minus 1. I need to compute that. And as I said, I'm going to use polynomial long division. If you prefer synthetic division, well, all synthetic division amounts to is leaving out so much information that you can't tell what's going on, but enough information that you can still run the algorithm of polynomial long division. So I'll just run the algorithm of polynomial long division. It'll take me more space and a little more time, but that's okay. I'll try to divide x minus 1 into 2x cubed minus x squared minus 7x plus 6. And I'm intentionally going to give myself lots of space. So I'm going to do this and talk through what polynomial long division is at the same time as doing it. So in order to do polynomial long division, I'm going to look at the biggest term in the divisor and the numerator. What do you need to multiply that x by to get 2x cubed? 2x squared. 2x squared. So that says that the first term in whatever this quotient is will have to be 2x squared. But 2x cubed minus x squared minus 7x plus 6 divided by x minus 1, there's no way that that's actually equal to just 2x squared. So what we'll do is we'll come up with a revised guess. We'll say, well, right now we're guessing that this is the result of division. In order to see how far off we are, well, if it were actually the result of division, this would be equal to that times that. So in order to see how far off we are, let's subtract that times that from the numerator. So I'm going to subtract
2x squared times x minus 1. So that's minus 2x cubed minus 2x squared, so plus 2x squared. And I'll get now a new guess for what this quotient should be. That'll leave me with minus x squared plus 2x squared, so that's a total of x squared. So if I can now divide x minus 1 into x squared minus 7x plus 6, I'll be good. I'll be done. So let's just repeat the algorithm again. What do I need to multiply this x by to get that x squared? X. So the next term in the division should be just x.
Positive x.
Positive x. And now we'll do the exact same thing as I did before again. So I need to now subtract x squared, because minus x times x is minus x squared. And then I need to subtract negative 1 times x plus x, leaving me with negative 6x. People feel okay so far? What do I need to multiply x by to get minus 6x?
Negative 6.
Negative 6. So, that should be plus 6x. So it's now minus 1 times minus 6. So minus 6. 6 minus 6 is 0. And borrowing language from long division of numbers, that means that the remainder after this division is 1. How do you feel about that? That seem okay? So let's now just summarize what this says. So what we've just computed is that 2x cubed minus x squared minus 7x plus 6 over x minus 1 is exactly equal to 2x squared plus x minus 6. Which might not seem that useful, but it will seem useful once you see that that means that 2x cubed minus x squared minus 7x plus 6 is equal to x minus 1 times 2x squared plus x minus 6. And remember, we wanted to set this equal to 0 and figure out what x is. Oops. So this is exactly equal to that product by the division we did. Do you suppose if we had more time it would be appropriate to multiply these together using a machine and see if it actually works out?
Sure.
That would be a good thing to do. I won't, but when you're doing your own computations, as soon as you do the division, see if multiplication gives you the right answer back. So instead of setting this equal to 0, we can set that equal to 0. But this now splits into two separate, easier equations. So we just need to solve x minus 1 equals 0. And we need to solve 2x squared plus x minus 6 equals 0. Do those both look like very easy equations to solve now? Yeah. What's the solution to x minus 1 equals 0?
1.
X equals 1, though the solution we already knew. Are the solutions to that easy to find?
Quadratic formula.
Use the quadratic formula. And, I mean, yeah, let's do it. So the solutions to that will then be x equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Negatives cancel. So if I can do arithmetic well in my head, that's 1 plus or minus root 49 over 4. I can zoom out a little bit now, can't I? So I mean, negative 1 minus 7 or negative 1 plus 7, each divided by 4. Guess that's negative 2 or 3 halves. So all of the roots to this all the solutions to this equation are x equal to 1, or x equal to -2, or x equal to 3/2. What do people think? Does that seem okay? So if you want to solve a high-degree polynomial equation, if you can find one root to the equation, you can do long division and reduce the difficulty of the equation you need to solve by 1. You can reduce a degree 3 to a degree 2, you can reduce a degree 4 to a degree 3, and so on. And as soon as you get down to degree 2, you're happy. You can do it formulaically at that point. So, let's do another one. So I think my intent will be, I'll talk through the solution to this first one, and then we'll see how you feel if you want more practice, and then we'll do the second one also. So let's try to solve the equation x to the 4th plus x squared plus x plus 1 is equal to 0. I claim that x equals -1 is a solution to that. Is it actually? I think so. Let's just plug in real quick. I've got space right above. -1 cubed is -1, -1 squared is 1, -1 is -1 plus 1. Yeah, that's 0. So because x equals -1 is a solution to that equation, what factor must this have? X plus 1. So let's do it. Let's divide x plus 1 into x cubed plus x squared plus x plus 1. And I guess let's do it. Let's just follow the algorithm. What should the first term in the result of division be? X squared, because I need to multiply x by x squared to get that x cubed. And now subtract the result of multiplication minus x cubed. And then it's 1 times x squared is x squared. I need to subtract that minus x squared. Oh, that's nice. The 2 terms we actually had to care about to do the subtraction just completely canceled. So what's the next form of the division? X. X. Yeah, I mean, I guess I was looking for a 0x squared, but maybe that's not even a term. Well, plus 0x, right? There are 0x squareds left over. So I just need to worry about this x. What do I need to multiply x by to get x? 1. So then I need to subtract Gesundheit. X and subtract 1. Oh, happily that works out to be 0. There is a remainder of 0. So let's write down what this means. So x cubed plus x squared plus x plus 1 is the same as x plus 1 multiplied by x squared plus 1. And we want to set this equal to 0 and determine what x is. Have we now made the equation very easy to solve? Yes. We have. We need to solve now x plus 1 equals 0, which gives a solution of x equals -1. And we need to solve x squared plus 1 equals 0. What are the solutions to x squared plus 1 equals 0? Ah, almost. You lost a sign. So you'll wind up saying, well, this should be the same as x squared equals -1. So x is, in fact, plus or minus the square root of -1. Which is I. So all of the solutions to this equation are x equal to -1, x equals plus or minus the imaginary unit. Did that make sense? People feel okay about this process?
it's got a fair number of moving parts, but all in all, not so bad. Especially if, say, you check your walk as soon as you do the division, if you do the multiplication to check if it's correct. I think that would be helpful. So there's one more example here to do. Trying to take this as for you. Maybe I'll give us 3 options. Either I skip by the example and just jump straight to the next line. I give you guys some time to just think through that with each other. Or I talk through one more. How many people want me to keep talking? Okay, that's enough hands. I'll keep talking. If you want to walk through this on your own, or even want to walk through this with the person next to you, do it. I'll continue talking.
So, I claim that x equals 5 is a solution. I guess a good first thing is you should never believe that I can do anything correct. So let's see if x equals 5 is a solution. 5 is too big a number to cube, because it's like 125, but that's too big a number. Let's just plug in. Let's evaluate 2x cubed minus 10x squared minus x plus 5, where x equals 5, and see what we get. Oh, come on. You're being upset because... Okay. Cool. 0. It works out. And so I literally just plugged in x equals 5. Plug in x equals 5, you get 0. Good. So now the next step is to do the long division. And in some sense, the long division is like the most fiddly step in this, and the step that's going to take the longest. How many people would like me to go through another example of just doing the long division? How many people want to see more long division? Okay, so that's one of the steps that people actually want to see. So maybe I'll do both options. I'm going to actually do the long division, and then I'll check it using a machine. Because, right, obviously, this is something that can be done by a computer. So let's see. So I need to divide. So x equals 5 is a solution. So what factor should I see? X minus 5 is a factor. So x minus 5, I need to see what happens when you divide that in to 2x cubed minus 10x squared minus x plus 5. Gesundheit. All right, so let's run the algorithm. What do I need to multiply x by to get 2x cubed? 2x squared. So the leading term in this division, in the result of division, will be 2x squared. And now all I need to do, what I should do is multiply 2x squared by x minus 5, subtract that, and use that to get a revised guess for what division should be, a second guess. So do that. You're going to subtract 2x squared times x, so that's 2x cubed. And then I need to subtract 2x squared times negative 5. So that'll be negative 10x squared. Cool. That works out to be 0. It's almost like I picked this example so that it would secretly be easy. What do I need to multiply x minus 5 by to get this 0x squared? Well, 0, I guess. So the next term in the division will be plus 0x, which I'll put there just as a placeholder. What do I need to multiply x by to get negative x? Negative 1. 2x squared minus 1. And now I need to multiply negative 1 by x minus 5 and subtract the result. So I need to subtract x times negative 1. So that's negative x, but I'm subtracting it so it becomes positive, plus x. Minus 5 minus 1 becomes positive, but then you subtract that. Minus 5. Oh, good. That walks out to 0. The remainder is 0. Excuse me. Thank you. Nice. So that means that we factored the thing that we want to solve. So the actual thing that we wanted, 2x cubed minus 10x squared minus x plus 5, is the same thing as x minus 5 times 2x squared minus 1. And we want to set that equal to 0 and solve. So now we can just read off the solutions. So you should interpret this as being like, this is maybe something that has a lot of computational moving parts, which is easy to screw up, so practice is good. But once you can do this, you can simplify the problem, and now solving this equation is super easy. Right, you split that into two equations, x minus 5 equals 0, or 2x squared minus 1 equals 0. What's the solution to x minus 5 equals 0? 5. That's the easy one. X equals 5. Do you think we could solve 2x squared minus 1 equals 0 easily enough? Yeah.
Isn't it negative 2x squared? Because in the start it's x negative 5, and then for you to go for negative 2x squared, isn't it negative?
Is this one negative?
Yeah, that's what I thought.
Well, let's see. So that 2x squared came from this piece. So where did that 2x squared came from? It came from saying, what do you need to multiply this x by to get that 2x cubed?
Yeah.
So I think that should be positive 2x squared. Yeah. And again, like what we'll do in a moment is we'll double check that by doing the division using a computer and also by doing the multiplication using a computer. So the result is x equals 5, or solving this, 2x squared plus 1 equals 1, x squared equals 1/2, or x equals plus or minus the square root of a half. How do we feel? That go okay? Especially once the division was done? Now, but maybe the division is hard enough that you aren't confident in your own results. So especially when you're doing things like homework, these are exactly the type of things you should ask a computer to do. You should do it yourself so that you understand the machinery. Let's see, 2x cubed minus 10x minus x plus 5 divided by so presumably if we've done the division correctly, this should walk out to be exactly the polynomial that we just saw. I lost a square. There we go. Cool. It says that the result of division is in fact 2x squared minus 1, which is what we got. So that's encouraging. It actually walked out okay. Nice. So, I don't think I'm going to do much more long division today because it's something that takes a while to do. And really the best way to learn it is by going through and reading the algorithm and then doing it. And that's hard to simulate in class with class time. So there are some suggested problems online to just have you go through. In the meantime, I think what I will do is start moving on to the next trick.
So in order to use this division trick, you need to have like an initial guess for what a solution to the polynomial is. But I've given you zero intuition about how to find that false guess. Well, here's a way to build some intuition. Let's try to find all of the possible rational numbers which might solve the polynomial. If we get like a finite list, we can plug in each member of that finite list. Well, and then just see if any members of our finite list actually solve it. Any one's solutions we do find will let us simplify the problem. So let's try to figure out this rational roots test. And let's do it by actually, so what I'll do is on this second page, I'll actually state the rational roots test. But in the meantime, let's actually see why the rational roots test is true by running the proof for a particular example. So here's a polynomial, 2x cubed plus 11x minus 7x minus 6 equals 0. Let's try to find all the rational numbers that solve that. So let's imagine any rational number p over q that solves this equation. We may as well put p over q in reduced form, so p and q shouldn't have any common factor. If they're both divisible by 5, you should cancel by 5. So just substituting in that p over q for x, that means that 2 times p cubed over q cubed minus, well, you see it in there and I can't possibly say it. That equation will wind up being complete. Everyone following me so far? So what I hope to do is to learn something about the interaction between p and q. So I'm going to start by, well, there's like lots of denominators around. I don't like fractions, so I'm going to clear denominators. I'll do that by multiplying everything by q cubed. If you multiply both sides by q cubed, you'll wind up with 2p cubed minus 11p squared. I'm going to multiply this by q cubed, but then I divide by q squared, so that leaves me with a q, minus 7pq squared equals 6q cubed. Okay, so that might look like it's just as disgusting as it used to be, right? But there's something that you can absorb here. Everything on the left-hand side is divisible by p. Everything on the right-hand side has a p in it. So that means p literally divides the left-hand side. But that means that p also has to divide the right-hand side of this equation, because they're equal, right? So what's the payoff? P divides into 6q cubed. But are p and q allowed to have any common factors? They're not. We put them in reduced forms at the beginning of the story. So any factor of p has to be a factor of 6. So p has to divide 6. What are all the whole numbers that divide 6? I guess it's like 1, 2, 3, and 6. That's only like 4 options. So that means of all rational numbers which solve this equation, there are only 4 possible numerators you might see. Do you think we could do something to get down to a finite list of denominators?
Yes.
Yeah. We could take this line and, well, let's rewrite it so that everything involving a q is on one side. And then we'll be able to get a similar divisibility thing. So let's take, I'm just going to write this equation down again because I'm going to do something with it. 2p cubed minus 11p squared q minus 7p q squared is equal to 6q cubed. So let's take that and put everything that has no q's on one side of the equation and everything that has some q's on the other. So we can rewrite that as 2p cubed minus equals, add this to the other side, equals 11p squared q, add this to the other side, 7p q squared plus 6q cubed. Is everything on the left-hand side divisible by q? Oh, no, the right-hand side, sorry. I'm looking this way. Good. That's that.
So everything on the right-hand side is divisible by q. So q has to divide into 2p cubed.
But again, p and q. So I've written that like particle bar is like this divides evenly into that. Are people okay with that? Just notation? I might use it again. All of that particle bar means is q divides evenly in. But p and q have no common factors, so q has to divide evenly into 2. What are all the factors of 2? 1 and 2.
So all the possible p over q's are, let's see, let's remember what the p's could be. They could be 1, 2, 3, or 6. Q's could be 1 or 2. So all of them are, let's see, there's 1 over 1 is 1, 2 over 1 is 2, 3 over 1 is 3, 6 over 1 is 6, and then we'll start dividing them by 2. 1 over 2, 2 over 2, 3 over 2, 6 over 2. Is there any redundancy in that list? Two over 2 is 1, and we already said 1. 6 over 2 is 3, we already said 3.
And in fact, there's something that we forgot about as we did this. 2 can be written as 1 times 2, so that's why 1 is a factor of 2. But 2 can also be written as negative 1 times negative 2. So there might be some negative signs floating around. So there are all the possible rational numbers that might be a solution to this polynomial equation. That's a finite list. It's only got it's got like 12 elements, right? So we could just check if each and every one of these is actually a solution to the equation. And that seems like a lot of kind of tedious walk. Fortunately, there are a lot of people in this room. And so I'm going to say, you guys plug in plus or minus 2, tell me what you get. Plug in plus or minus 3 to the original polynomial, tell me what you get. Plus or minus 6. Plus or minus 1/2. Oh yeah, and you should definitely use a machine, unless you want to do like computations by hand. I guess like 2 isn't so big a number, so you guys could probably do yours by hand. So, as you plug in any of the numbers, let's see, plus or minus 2, do those solve the equation? Either of them? Okay. Plus or minus 3? Both no? Okay. Plus or minus 6?
-6.
Negative 6 does the job. Plus or minus 1/2? Well, cool. So I'm going to show you, because you're probably like taking a calculator and plugging things in. let me show you a way of repeatedly doing this stuff once you know the notation using Wolfram Alpha, which uses the same language as Mathematica, if you want to use that. So you can ask it to evaluate a function where x is equal to 1 of some sequence of numbers. So there's plugging in the result of 1 and -1. Do I get 0 either time? So 1 and -1 are out. Let's do 1/2 and -1/2 to see what we get. 1/2, -1/2. This shouldn't be taking this long. All right, are those 0? No. Is there any more that we have to do, or is that it? 3 halves. Has anyone just already done 3 halves while I've been stalling? Okay. Happily. So especially once you get that finite list, as long as it's not like 10 trillion long, you can just ask your computer. Are either of those 0? So we have now found all of the rational solutions to this equation, namely x equals -6. So we won't actually do it, but could we now run the machine that we've built to completely solve the equation we started with? Yeah, we could say, well, x equals -6 is a solution, so x plus 6 should be a factor. Divide x plus 6 into this thing, you'll get a degree 2 polynomial out. Use the quadratic formula now. Because you know the answer won't be rational. There are no more rational solutions. So here's the actual statement of the rational roots test. So if you like, the machinery that we did to do that walkabout, oh, this is going to divide p, that's going to divide q, that could be done for any polynomial. Any polynomial you want. And if you do that, you'll eventually find, if you have a polynomial equation, a sub d x to the d, a d minus 1, x to the d minus 1, and so on, all the way down to x0, then p, which is the numerator, must divide a0, which is the constant term, so the numerator p has to divide the constant term, and q, the denominator, must divide AD, which is the leading coefficient. How do people feel about that? That's now a tool that we can use. The reason that this tool works is because of exactly that analysis above. But let's just use this tool to find all possible rational solutions to that equation. 3x cubed plus 2x plus 1. So let's just list all the possible values for p, all the possible values for q, and write down the quotient. So all possible values for p. So p, the numerator of p over q, has to divide the constant term. What's the constant term of this polynomial? 2. So we see p has to divide 2. What are the factors of 2? Well, that's a stupid thing to ask. P has to be either 1 or 2. The possible values for q. Q has to divide the leading coefficient of the polynomial. So what does q have to divide? 3. So q has to be a factor of 3. 3 doesn't have very many factors. Q is either 1 or 3. So all the possible values for p over q are 1 over 1, 2 over 1, 1 over 3, or 2 over 3. But they might have plus or minus signs. What do you think? Should we go through and, well, so either way, we're going to check if these are solutions. maybe what I'm going to do is I'm going to say, let's check if these are solutions in the most efficient way possible by using a computer. And in fact, let's use the computer in such a way that you don't have to evaluate 8 expressions one at a time. That wouldn't take that long. If you're quick, probably in this time I spent stalling and speaking, you could have done it. I'll use this sort of language where I'm just going to ask Wolfram Alpha to evaluate this polynomial 3x cubed plus 2x plus 2, where x is equal to, and now I'll list all of the options. 1 minus 1, 2 minus 2, 1/2 minus 1/2, 3/2 minus 3/2. Yeah, thank you. Oh, apparently I screwed up the notation anyway. 1/3 minus 1/3 and 2/3 minus 2/3. I don't know why it's being annoying about this. So, at the very least, 1 and minus 1 don't form solutions. Oh, I've got enough time. Let's actually finish this. Technical difficulties be damned. Second option is 2 or minus 2. All right, are those 0? Nope. So those are fine. X equals 1/3 or negative 1/3. So if this was a waste, how many people at this point using their handheld machines had already done all 8 computations? Oh, good. Any of them solutions? Okay. None of them are. Cool. So this is something that can happen. It might happen that there are, in fact, no rational solutions to your polynomial equation. So what do you think? When you determine that there are no rational solutions, can we go to the next step? Do we have anything we can divide in? No, we're screwed. The plan of attack that we have right now just won't work. The best we can do is numerical methods. We can graph it, we can zoom in on the roots. But we will never get exact values using the tools we have. Nice. So maybe I'll describe what's posted to the web page for today. There's a supplemental document in which I do my best to talk through very slowly polynomial long division. You might take a look at that if you want to. It also includes a survey of synthetic division, if you want to see the translation between polynomial and synthetic. I have posted an extra credit in which you will explore the cubic formula and find that it's a formula that is long, and some homework. I think that's all that I posted. I'll see if I can track down that email.
It was like the first day, like this semester or the second.
Okay, so you were very proactive.
I was. Not enough to come and actually talk to you, but.
That's okay. I mean, this is the right time to tell me.
Okay, okay. All right. Just thinking
Yeah. Yeah, absolutely.
Where in Canada are you from?
Calgary.
Okay, where's that?
It's in Alberta. It's straight north from Montana.
That's cool. My cousin, he lives in Windsor, so technically, well, it's 5 days, right? You can actually see it.
Oh, yes. Yeah.
I'm like,
I don't have to.
yeah, I've heard that's in Canada. It's like one little island.
Yeah, I mean, I'm sure the people who are there know what country this is.
Oh, no, they do. Yeah, they do. How's it going?
Good, yourself?
Does your class not meet Thursdays?
No, just Monday, Wednesday, and Friday. Do you every day?
No, not Tuesdays.